Most of our modern infrastructure is built to fail. When steel and timber are placed in high moisture environments, they inevitably rot or rust. Eventually, the structural supports buckle under monsoon flash floods. But in the forests of Meghalaya, India, there is a biological alternative. Known locally as Jinkyang Dri, these living root bridges don't collapse as they age. They stay intact and continue to grow for over 5 centuries. This durability is a necessity of geography. Meghalaya contains some of the wettest places on Earth, creating a climate so aggressive it can dissolve standard civil engineering projects in a matter of decades. To understand the difference, look at the depreciation cycles. Traditional concrete is designed with an expiration date, represented by this declining curve that weakens over a century. The living bridge follows an upward trending growth curve. Modern infrastructure is built as a static object that begins to deteriorate immediately. To solve the problem of decay, engineers are looking at biological systems that are designed to do the opposite. These structures are the result of a sophisticated indigenous practice, pioneered by the Khasi and Jaintia peoples of Meghalaya. The process begins when villagers take the young aerial roots of the Indian rubber fig and train them across temporary bamboo scaffolds. Over decades, these roots grow across the river and anchor into the opposite bank. As the roots cross paths, they undergo inosculation, a natural grafting process where separate branches fuse into a single cohesive lattice. Because the bridge is alive, it is self-repairing. While inert materials weaken as they age, this biological lattice actually thickens and deepens its root system over time, increasing its load-bearing capacity. This creates an economic inversion. The primary investment isn't money or high-carbon materials, but time. The bridge is sustained not by corporate maintenance contracts, but by the community itself. The Jinkyang Dri demonstrates that infrastructure can serve a community for half a millennium when it is driven by intergenerational stewardship. Researchers are now analyzing these ancient bridges to extract their structural secrets, using drone mapping to see how living systems manage weight and stress. This research forms the basis of a discipline called biombotanic. It aims to integrate living trees directly into buildings as load-bearing architectural members. By using 3D photogrammetry, scientists can quantify exactly how root fusion and anisculation responses vary under different physical loads. This allows for hybrid scaffolding. Designers use temporary steel to carry the weight until the young plants mature enough to take over the load-bearing capacity themselves.
This biological approach solves modern urban crises. Cities face extreme flood events and rising heat, challenges that traditional concrete channels often exacerbate. While concrete banks crumble under the pressure of a surge, the root networks of the Indian rubber fig naturally lock the soil in place. They act as anchors that prevent erosion during extreme flash floods. Above ground, these living structural networks provide secondary microclimate benefits. Their canopies release moisture through evapotranspiration, cooling the air for the people below. The thermal profiles of these structures show a stark contrast.
While a concrete bridge absorbs solar energy and radiates it back into the city, the living canopy bridge provides continuous cooling. To survive a changing climate, we may need to abandon infrastructure that fights against the natural world. If we want our cities to last, we must adopt generational stewardship and plant the cities of tomorrow.